to another AQA chemistry video. Today I'm going to be doing a video on Hess's law. Hess's law allows us to understand and be able to easily calculate enthalpy changes. So I've got an example here, right? So when you think about Hess's cycles or enthalpy change, I'm going to go to Hess cycles later on, but the idea of Hess's law, right, is that I'll read out this little statement here, right? Hess's law, the enthalpy change, what it actually is, right, is that the enthalpy change of reaction is independent of the reaction pathway. That's the definition, by the way, that's the definition. The enthalpy change of a reaction is independent of the reaction pathway, meaning the enthalpy change of a reaction is the same for if the reaction is direct or indirect. Now, I've got this little diagram here, right? I want you to think of this like vectors, right? Think of it like a vector, right? So you have, let's say A to C is a reaction, but A to B, you could have a side. If you want to go from A to C, you could just go straight, or you could have a side reaction. Let's say you originally found you wanted to create a product, right? But the only way that you knew, or the only way you was able to measure from A to C was going from A to B and B to C. There's other reasons why, but let's just say, for example, like that is that, right? And there's delta H. Let's call this delta H1, delta H2, or enthalpy change 1, and then enthalpy change 1, enthalpy change 2, enthalpy change 3, right? And also, if we're going from vectors, right, we know that if we want to get delta H3 directly, we have to do delta H1 plus delta H2, right? So delta H3 is equal to delta H1 plus delta H2. So if this is, for example, 5 kilojoules per mole, and that's 6 kilojoules per mole. 6 kilojoules per mole, and that's 5. Then if you wanted to work out what this is, if we weren't able to calculate what delta C is, because it's maybe the reaction might be difficult to work out the enthalpy change for this reaction. We already discussed in previous videos why it may be difficult to experimentally find out the enthalpy change of a reaction. But let's say it was easy to work out from A to B and B to C, and we know what A to B is and know what B to C is. We already have this here. Enthalpy change, or the enthalpy change for this reaction would be 5 plus 6. Enthalpy change 3, 5 plus 6, and that's 11 kilojoules per mole. The reason why we know this because of Hess's law. This is a well-known law. It's proven that the enthalpy change of any reaction is independent of any reaction pathway. So it means that to go from here to here is the exact thing. As I said before, this is why I said think vectors. Exact same principle. To go from here to here is the same as going from here to here and here to here. So, and that's why you need to actually think about Hess's law, right? That's all it is, and it just makes it easier for us to calculate these reactions. So what does this mean, right? Hess's law is used for obtaining enthalpy changes that aren't directly observable. These are often obscure reactions. With the help of some easy reactions that involve some of these compounds, we can derive the enthalpy changes we're interested in. And so, hence why this is pretty much just saying what's going on here. So we can just work out, if we don't know what A to C is, but we want to work out, we need to work out what A to C is, but we know what A to B is, we can easily work out what A to B is and what B to C is. We use Hess's cycle, we can use Hess's law and Hess's understanding, or Hess's law, I should say, to work out what A to C is by going through that route. And I said, this is very similar principle to vectors. So breaking it down, right? So this means that the following will all have the same enthalpy change. So if I want to go from A to E, I'll have to go from A. It's the same as going from A to B to C to D to E, or A to C to E, or A to E, right? It's all the same thing. It all equals the same thing. Overall, they all just convert A to E, and so the overall enthalpy change will be identical for all of them, right? So if I want to go from A to E, I mean, I'm not saying I want to go to hospital, but, you know, I don't know why I said that joke. It's kind of dead still. That. So if I want to go from here to here, right, but we don't know what this is. Let's say we aren't able to know what going from here to here is, right? But we know what A to B is. We know what B to C is. And I think you can get what I'm trying to say here. B to D is. Actually, I want to do this all in in white. We know what the enthalpy changes for that reaction from A to B, from B to C, from C to D, and then from D to E, right? All of this going from all around the circle is the same as going from here to here. And this is just following that vector rule. And even if for example, like let's say for example, right, we don't know, let's say for example, we don't know, that's this is what I've just drawn here. What I just drawn here is what this is here. So A to E is the same as going from A to B to B to C to C to D. If you add them all together, that would be A to E, right? Actually, I'll write out what it is here. Right, so the enthalpy change to go from A to E is equal from going from A to B plus B to C plus C to D plus D to E. Hopefully I've said it enough times and you can just get the idea of what I'm trying to say, so I don't have to keep repeating it. I think it's pretty obvious what's going on here, right? But some people might get confused by the small factor of this. If you know vectors, then this isn't a problem for you. If you've done maths, then this isn't really a problem for you. But let's say you get this situation here, right? You think, oh no, but I can't go from A to B to C to D to D to E. Then you just take it, to go from, let's say it's let's say this is 8, right? 8, 7, 6, and 5. So to go from A to E, it's same as vectors, right? So from A to E, 8 plus 7 plus 6. But to go from here, from D to E, would be minus 5. So it'll be 8 plus 7 plus 6, and then minus 5. And then that would be equal to what A to E is. But this is just an example of just showing you what it is, how it all works, and generally, if you know vectors, it's kind of the same principle. Hess cycles. So we can use Hess's law to derive Hess cycles, which will help us with calculations. We can create cycles using enthalpies of formation or combustion. Hess cycles. Above shows how we can convert the principles of Hess law into an actual equation. So we can set up an equation using the pathways delta H1 plus delta H2 equals delta H3. And we can then substitute in the known values and rearrange to find the unknown values. Using enthalpies of formation. So the first type of Hess cycle is those that use the enthalpies of formation to calculate the overall reaction enthalpy change, right? As I said before, so we set up a cycle as shown, which includes 2 enthalpies of formation arrows to create the cycle. To do this, we must know the enthalpies of formation for the reactants and products. The enthalpy of formation for any element is 0. So the enthalpy of formation of any element is, as I said, that is 0. This is important here, right? So in a question, they might ask you to work out the enthalpy of formation using the Hess cycle, but they don't give you the enthalpy of formation from element to element, and that's because the enthalpy of formation between elements is always 0. If we're going from Cl2 to Cl2, it's just 0, right? But this is an example, right? So if they wanted to go from, goes from your elements to your reactants to your products. Usually it's actually, you get it'll be kind of like flipped. Like it'll be you have your elements here, your reactants here, and then your products. So it wouldn't be just like this perfect arrow circle here. It would be more like so for example, elements, reactants. Actually, can I just draw this down? I could just draw this down, right? There we go. Elements are here. Reactants products. Now I would get an example of one, but I was like, I'm just not bothered to go through one. But so if this is more what you would get, right? And they'd ask you to go from here, from your reactants to your products. I need to realize if I want to go from here to here, and if I want to go from here to here, I need to do minus this and then plus this. Vectors, right? It's just vectors. And this is from elements to reactants as bond forming, so be an exothermic reaction. So this would just generally be a minus value, so minus X kilojoules per mole. And then this would be from elements to products. I mean, this would also be a negative reaction here, but minus X kilojoules per mole. But you're doing minus and minus, that's plus, and however much this X is here, I'll say, let's call this minus Y, right? So in this case, it would be to go from reactants to elements to products, would be minus X plus minus Y. That's just X minus Y. You get what I'm trying to say here. I'm not trying to confuse you with this, but I could use actual numbers, but it's just to show you that it's the same as vectors. Reactants to elements to products here, but this is more or less what it would actually look like in your exam. It wouldn't more look like that because it's kind of like a perfect flowing triangle. It's but yeah, that's just what you need to understand. Hopefully this didn't confuse you. If this confused you more, forget about it. Just go back to what I said here when I was talking about the vectors or this example here. If this confused you, hopefully this made it easier, but if it didn't make it easier, just go back. So using enthalpies of combustion, we can use a similar method to set up a cycle using enthalpies of combustion. So below is the enthalpy change 2 and enthalpy change 3, representing enthalpies of combustion, and this can be spotted by the combustion of products CO2 and H2O. So we know it's a combustion reaction because we have CO2 and H2O as the products. So usually when you're doing these, you have to balance these out. I think this is balanced, but that's something you need to take into consideration when if it's not balanced, then you have to balance it, and if it's changing, you have to multiply this value by how many you've multiplied it by. But I'm not gonna try. I'm trying not to confuse many people here, but make sure that your cycle is balanced, right? And yeah, this is it. Should I get the equations of this? You'll see it in a reaction question. I'll probably get a question. I mean, enthalpy of combustion, generally it's reactants minus products, whereas enthalpy of formation, it's products minus reactants. So that's what you need to, enthalpy of combustion. I'll write actually here. Enthalpy of combustion equals the enthalpy combustion of reactants minus the products for combustion, enthalpy of combustion. Enthalpy of formation. What's that all about? What's this? That's okay. Well, that's bugging out now. Okay, cool. Don't know what happened there, but that was a slight bug. Why did I scream like some little girl, fam? She's so moist. Anyway, enthalpy of formation. Make sure to put that little. I should have put the little feet here to show that it's under standard conditions. And that's enthalpy of formation of your products minus your reactants. Hopefully this video was helpful, and that's it.